All right, so we're going to pick up with our next section now and continue looking at what happens with elements in terms of the periodic table, as well as those elements and how they arrange their valence electrons. And so valence electrons, again, are just electrons in the outermost energy level of an atom. And it turns out the valence electrons are really important in determining how that atom is going to interact with other atoms or molecules, or whether it won't interact with other atoms and molecules. So that's a really key component of this, is those outer shell electrons. They determine how reactive something is. And so it turns out that for something that's very non-reactive or very stable, its outermost shell is going to be completely filled with electrons. And so for something like helium, which is number 2 on the periodic table, helium has 2 electrons in the outer shell. The outer shell will only hold 2 electrons, and so therefore for that reason it's very, very stable. Everything else below helium in that same column on the periodic table are what we describe as being inert, and everybody else in that column also has a full outermost shell of electrons. So for them, it means they have 8 electrons in their outermost shell. So that brings us to something called the octet rule. And the octet rule says that elements, atoms, tend to be most stable when their outermost energy levels are completely filled. And so if an atom comes to the table without an outer shell that's completely filled, the only way for it to fulfill its octet rule and become stable, non-reactive, inert is by reacting with someone else. And so that might mean accepting electrons, it might mean giving up electrons, it might mean sharing electrons. But any of those 3 options might be a way for an atom to satisfy its octet rule and keep the outermost energy level completely filled. Right? So that's going to take us into chemical bonds. Right? So molecules then are collections of atoms, and molecules can have atoms that are of the same element, or it can have atoms of different elements. So for example, water, which of course is H2O, is an example of a molecule. It's got 3 atoms, 2 H's and 1 O, therefore it qualifies as a molecule. Oxygen gas, which is O2, also qualifies as a molecule because it has 2 atoms. And really to be a molecule, you really only need to have 2 or more atoms. Compounds then are a little more specific than molecules. Compounds have to have not only more than 1 atom, but more than 1 type of element. So whereas H2O is both a molecule and a compound, O2 is a molecule but not a compound, because with O2 you just have oxygen, and like I said a second ago, to be a compound you have to have more than 1 type of element. Right, so what this next section is going to look at is how molecules and compounds are held together. Generally speaking, throughout the rest of this lecture, I'm going to refer to as aggregations of atoms as being molecules, because molecules is a more all-inclusive sort of a term. It's less specific than compound, so you can use molecule and be correct more than if you use compound. So that's kind of the convention I'm going to use in the rest of this lecture. All right, so as I mentioned in the previous section, the way atoms can fulfill their octet rules and therefore become more stable, and it's all about becoming stable. If you're an atom reacting with someone else or a molecule reacting with someone else, generally speaking, the universe likes stability and it doesn't like instability. And so anything that can happen to make something more stable is going to be favored energetically. Okay, so for atoms that need to satisfy their octet rules, for atoms that are looking to fill up their outermost shell with electrons, that's going to mean giving up electrons, accepting electrons, or sharing electrons with other kinds of atoms or molecules. All right, so that's going to lead us to chemical bonds. The reason why bonds happen and the reason why things react the way that they do is so that they become more stable, and so those octet rules are going to be satisfied. Okay, so the overall idea here is that we're trying to get to a lower energy state. There's a relationship in nature that says things that are very high energy tend to be very unstable, and things that are low energy tend to be very stable. And so for that reason, the general tendency of the universe is to go from more unstable and higher energy kinds of things into more stable and lower energy kinds of things. And so that's why reactions happen. Okay, so we talked about stability, we talked about valence shells, we talked about the octet rule. Right, so for things over here on the periodic table, in this very last column over here, everybody in this column has their octet rule satisfied naturally. Helium, neon, argon, krypton, xenon, radon, all of them have their outermost shells completely filled, therefore they're already very stable. And for them, if they were to react with somebody else, they would actually become more unstable, because then they would have an outer shell which was not completely filled with electrons. If neon were to give up 1 electron, it would only have 7 in the outer shell. It would be less stable. So under normal conditions, then neon isn't very likely to give up an electron or accept an electron, because if it does that, it's going to be less stable than before it gave up or accepted that electron. And like I said before, the universe likes stability. The universe is always driving toward more stable types of situations. Everybody else in the periodic table doesn't have their outer shell completely filled, and the only way to approximate that or to get there is by having some sort of reaction and giving up, sharing, or accepting electrons from other kinds of things. Okay, so if we take a look at water, water is a really important molecule, as we're going to see in this chapter. Water is, of course, H2O, which means two hydrogen atoms and one oxygen atom bound together. Oxygen is number 8 on the periodic table, which means it has 2 electrons in the first shell and 6 electrons in the outer shell. So that means for oxygen, it either needs to pick up 2 electrons or lose 6 electrons to have the outer shell completely filled. And so, as you might expect or predict, it's much easier to find 2 electrons and accept them than it is to give up 6 electrons to someone else. So oxygen then is going to tend to try to get electrons from other kinds of things, either by sharing or by more or less permanently accepting electrons from other sorts of substances. Hydrogen, on the other hand, only has 1 electron in the outer shell, and so for this circumstance, hydrogen is trying to find an electron also so that it can have its outer shell completely filled. Of course, with hydrogen, then it would be 2 electrons in the outer shell because it's relatively small. And so if we take these two H's and this one O and put them together, that means they're going to be relatively more stable. H by itself is less stable than H2O. O by itself is less stable than H2O. When you put them together, stability is increased, and energetically, the energy goes down because they're more stable. Okay, so what happens here is something like this. We're going to create what are called covalent bonds, where the hydrogens and oxygens are going to share electrons back and forth, thereby satisfying everybody's octet rule. Okay, so if we take a look up here at carbon, actually we'll do oxygen first, as we just talked about it. Oxygen is number 8 on the periodic table. Atomic number is 8, which means 8 protons and 8 electrons. Okay, so 2 in the first shell, 1, 2, 3, 4, 5, 6 electrons in the outer shell. It needs 2 more electrons to achieve stability. Hydrogen has 1 electron in the outer shell, as does this one. These two each need 1 more electron also to achieve stability. So if we take this electron here and plug it in with this, and this electron here and plug it in with that, we create what's called a covalent bond. If we plug this electron here, there, and plug in this electron over here, that's a second covalent bond, and so that creates H2O. Now if we look at this picture, if we take a look at oxygen at least part of the time, oxygen's going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer shell. It's stable. Hydrogen, on the other hand, will have 2 electrons in the outer shell. It's stable, and the same thing is true of that hydrogen as well. It's going to be stable because it has 2 electrons in the outer shell. Remember, the first shell can only hold 2 electrons, so for something like hydrogen or helium, having 2 in the outer shell means their outer shell is completely filled. If we look at carbon, carbon's number 6 in the periodic table, so we have 2 electrons in the first shell, and then 4 electrons in the outer shell, so 6 electrons total, 1, 2, 3, 4, 5, 6 total. If we take 4 H's, each one of them also needs 1 electron. They kind of match up pretty well. So we plug this one in here, this one in here, this one in here, and this electron in over here, and that's going to give us methane. So again, if we take a look at this more closely, carbon, at least part of the time, is going to have 2, 4, 6, 8 electrons in the outer shell, and each one of these hydrogens will also have 2 electrons in its outer shell, so all 5 partners are stable with this association here. Right, so covalent bonds are sharing of electrons. Valent refers to valence electrons, their outer shell electrons. Co means together, or in this case sharing. Covalent bonds are when atoms share at least 2 valence electrons with each other. The overall molecule itself does not have a charge, okay? But what turns out that can happen is that certain parts of the molecule can have what's called a partial charge. The overall molecule itself, if we were to look at methane, if we add up the number of protons, 1, 2, 3, 4, plus 6 is 10 protons. We have the electrons, 2, 4, 6, 8, 10 electrons. It's balanced. The entire molecule has no net charge. Same thing with water. There's a total of 10 protons, and we add up all the electrons, 2, 4, 6, 8. There's 10 electrons as well, so it's going to be balanced with no net charge. All right, so by doing this, we have molecules with no charge, where the partners in the association all have their octet rule satisfied, and typically we end up with no unpaired electrons. Electrons really like traveling in pairs, and when they're solo or by themselves, they tend to be less stable than when they're partnered up with someone. Now, the issue that can occur here, it's not really an issue, but the pattern that can occur here is that when you have 2 or more atoms sharing electrons, sometimes they don't share equally. And everything in this entire chapter, that is probably the single most important thing we're going to talk about. In covalent bonds, which are the more common type of bond in a living organism, the sharing of electrons is not always equal. Sometimes one of the 2 partners gets to be a bit of a bully and hog the electrons. They get the electrons 75% of the time, and the weaker partner only gets them 25% of the time. And that's going to create some very important chemical properties. That is something that's true of water, as we saw in the last slide. Not true of methane, as it turns out, but definitely true of water. And that's one of the things that gives water some of its very important properties, is the fact that the electrons are not shared equally between hydrogen and oxygen. Now you can also have covalent bonds that occur in groups of more than just one. You can have double covalent bonds, you can have triple covalent bonds. That's also something which occurs, and the reason is the same. The atoms involved are trying to satisfy their octet rules. Okay, so if we take a look at something called electronegativity. Electronegativity is a measure of how strongly an atom attracts electrons. Another way of saying that is it's the affinity of an atom for an electron. It's how strong or how tightly it holds on to those electrons when other things try to take the electrons away. Okay, so if we have things with very different electronegativities, something like in this picture here, we've got oxygen with electronegativity of around maybe 3.4. We have hydrogen around maybe 2.2, 2.5, somewhere in there. That's that neighborhood. These two H's and O's have very, very different electronegativities, which means that when H's and O's share electrons, the electrons are going to spend more time with the O than they do with the H. And so we end up with an asymmetrical sharing of electrons, which again gives water some very, very important properties. If we look at something like hydrogen and carbon, these two have very similar electronegativities, so when they share electrons, they tend to share almost equally. The carbons get them a little more of the time, but the hydrogens also get the electrons for a good bit of the time as well. So it's going to be a more equal or symmetrical sharing of electrons with that association. Right, but with the asymmetry of sharing of electrons, that's going to create some very important potential for chemical properties that are very substantial and important and significant for all kinds of living organisms. Right, so if we take a look at water again, and as we said, water has a grand total of 10 protons and 10 electrons. So collectively then, the entire molecule does have a zero net charge. It's no charge overall. But the fact that oxygen and hydrogen do not share electrons equally means that certain parts of the molecule will have a slight charge or a partial charge. In particular, because oxygen has a higher electronegativity than hydrogen does, the electrons are going to spend more time hanging out up here with oxygen than they do hanging out down here with hydrogen. Right, so if we imagine that maybe 80 or 90% of the time, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons up here, but only 8 protons, because we know oxygen has 8 protons. 8 protons most of the time, 10 electrons most of the time, means this end of the molecule up here, the oxygen end, is going to take on a slightly negative tendency. Meanwhile, down here on the bottom, if the electrons are hanging out with oxygen, that means they're not hanging out with hydrogen. So 80% of the time, or 90% of the time, there's going to be 1 proton here and 0 electrons. And the same thing over here, 1 proton and 0 electrons. So most of the time, there's going to be a slightly positive charge down here on this end. Right? Now, again, the overall molecule is neutral, but within the molecule, there are regions of partial charge that create some very important chemical properties. All right, so we take a look at covalent. What does covalent mean? It is sharing of outer shell electrons. Now, when the electrons are shared equally, we call that a nonpolar covalent bond. And nonpolar covalent bonds are important. Nonpolar covalent bonds create molecules that are water insoluble. They are what we describe as being hydrophobic. They do not dissolve in water. They don't like to mix with water. So oil, for example, molecules are held together with nonpolar covalent bonds, and those molecules do not interact with water. They separate from water because they have different types of bonds. Water has polar covalent bonds, oil has nonpolar covalent bonds. They don't mix real well. There's a really good rule of thumb that says like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Nonpolar and polar do not get along very well at all. Okay, so nonpolar covalent bonds are an equal sharing of electrons. Polar covalent bonds, on the other hand, result in an unequal sharing of electrons. So if you have something like hydrogen sharing with another hydrogen, since they're basically the same thing and have the same electronegativity, that's going to be a 50-50 sharing. Both atoms are going to get the electrons roughly half the time. Versus water, where you've got hydrogen sharing unequally with oxygen, that's going to create some polarity, which means water is going to be something which has partial charges, and anything else that has partial charges or even full charges, like ions, can dissolve in that water. So that's going to be some very important chemical properties that we're going to see as we move forward. Right? So we talked before about H2. H2 represents a sharing of a single pair of electrons. Half the time these two electrons hang out over here, octet rule satisfied. Half the time the electrons hang out over here, octet rule satisfied. So that's going to be a fairly stable association. It's much more common to find H2 than it is to form just H out in the environment because it's much more stable in this form. Now, I mentioned before briefly, you can also have double bonds. Right? If you have oxygen sharing with another oxygen, what they'll do is actually share 2 pairs of electrons, 4 electrons total, and create a double covalent bond. Nitrogen gas actually forms 3 bonds with other nitrogen gas or atoms. So you get a grand total of 6 electrons bouncing back and forth, what is otherwise called a triple bond. And typically, you don't go above that number of bonds, but those are also somewhat common in nature. Carbon sharing a double bond with oxygen, oxygen sharing a double bond with something else, nitrogen sharing a double bond with something, or triple bond with something. Those are all fairly common types of associations. All right, we're going to get back to polar and nonpolar a little bit later and review that because, like I said, that's an incredibly important thing for this course and all the things we're going to be talking about here coming up soon. Ionic bonds are less common in living organisms, living systems or cells. And so with an ionic bond, the attraction that occurs not as a result of sharing of electrons, but as a result of a transfer of electrons. So if you have an element or an atom that gives up a single electron, it's going to take on a +1 charge. So imagine sodium. Sodium is number 11 on the periodic table. If sodium gives up 1 electron, it's going to have 11 protons, but only 10 electrons. 11 pluses, but only 10 minuses, therefore it takes on a +1 charge. Chlorine, on the other hand, is number 17 on the periodic table. Chlorine has 7 electrons in the outer shell, which means chlorine really likes to accept an electron. And so if it does that, chlorine then has 18 electrons, but only 17 protons, which means chlorine takes on a -1 charge. Right? So what that does is it creates an Na+, or a sodium ion, a Cl-, or a chloride ion, and there's going to be attraction there. Opposites attract, opposite charges attract, and so we're going to get a bond forming between sodium and chloride. Right, so this type of bond is very common when it comes to metals. There are cases when these bonds are important in living systems, especially when we start dealing in ions that our bodies and cells need to function. So sodiums, chlorides, potassiums, magnesiums, calcium, those are some really important ions when it comes to living organisms. The other thing about this is that because these involve ions which have charges, ionically bound compounds or molecules can also be disrupted by water. Since water has partial charges, the bonds, covalent bonds, which are nonpolar or which are polar in water, are able to break apart ionic compounds. So obviously, if you take salt, dump it in water, it dissolves. The reason for that is the partial charges on the H2O mess with the full charges on the sodium chloride. So it breaks apart those and allows that to dissolve. All right, so we take a look at sodium. I mentioned this a second ago, but just to go through it again really quickly, sodium has 1 outer shell electron. Its choices are either to give up 1 electron or to try to find 7 electrons. Giving 1 up is a lot easier than trying to find 7, so it does that. It gives up 1 electron and takes on a +1 overall charge. Chlorine has 7 in the outer shell, so it can either choose to gain 1 electron or give up 7 electrons. In the situation similar, it's much easier to accept 1 than it is to give up 7 of those electrons, so that's what chlorine does, to become a chloride ion. All right, so this is what it looks like. We've got this transfer of this last electron in the outer shell of sodium over here. Now if it does that, this outer shell goes away and we're left with 2, 4, 6, 8 electrons in the outer shell, and as we know, that's going to mean that the octet rule is satisfied, and now it's going to be more stable than it would be otherwise. Chlorine, on the other hand, picks up the electron, and now it's going to have also 2, 4, 6, 8 electrons in the outer shell. It's also more stable than what it was before the interaction took place. So with this plus charge and this minus charge, we get attraction that then allows for the ionic bond to form. All right, the last topic we're going to talk about in this section is what's called a hydrogen bond. And hydrogen bonds happen whenever you have polar covalently bonded atoms or molecules bound together. And so what happens is that hydrogen bonds form between polar molecules, and these hydrogen bonds are very weak, they're very transient or temporary, but what tends to happen is that when they form in enormous quantities. Thousands, millions, billions of hydrogen bonds form in a very, very small volume of some substance. So when you have a lot of them, even though each one is individually very weak, if you have enough of them together, collectively then they're very strong. Right? So some of the things that we're going to see in this course that are bound by hydrogen bonds. DNA. The 2 strands of DNA, the double helix of DNA, is held together in the middle by hydrogen bonds. Proteins sometimes are reinforced or strengthened by the presence of hydrogen bonds. These bonds can be very, very important. A lot of the special properties that water has happen because of hydrogen bonds also. So we're going to see this term popping up quite a bit. So it's really important you know what a polar covalent bond is and also what a hydrogen bond is and how that affects organisms' molecules that they have. And here we've got a water molecule, 2 water molecules, right? So we've got a molecule here with a partial plus end on the hydrogen, partial minus end on the oxygen. If we line that up with another water molecule with a minus charge on the oxygen and a plus charge on the hydrogen, with a partial plus and a partial minus, we get a linkage. That linkage is a hydrogen bond. It is by no means permanent. It is by no means strong, but when you have enough of them together, collectively they take on a sort of collective strength that otherwise they wouldn't have on their own. So it's very, very important. This is a water molecule again, right? We've got these two electrons being shared between oxygen and hydrogen. These two shared also between oxygen and hydrogen. Thing is, these two electrons spend way more time up here than they do down here. And these two electrons spend way more time up here than they do down here. So that means the vast majority of the time, this end here and this end over here are going to have a partial plus charge. 1 proton, but 0 electrons takes on a partial plus charge. The other end is going to have 10 electrons, but only 8 protons, so it's also going to take on a slightly minus charge. So if you take this water molecule and line it up with other water molecules, what you'll get is the lining up of the partial plus end on the hydrogen with the partial minus end on the oxygen, and a hydrogen bond is going to form. All right, so we'll cut this off here, and I will start up another section momentarily.